Am I making noise? I am making noise. Welcome. Today, it's a Sunday, felt like a break. I'm going to use my break to derive everything. Is it deleting? In the free blue one brown videos. On neural networks. So these videos I really recommend. This is an opportunity to watch them if you've never watched them before, but also feel free to go watch them at your own pace. We are gonna just stop every time there's derivation, every time there's a kind of thinking point, and work it through for ourselves. Because I think the step, no sound. I think the step through to active learning with this is such an important step. Like, you shouldn't feel like you need to go through to active learning right at the beginning. Very, very quick thing on what I mean by active versus passive learning. This is a not perfect dichotomy, but it's the difference between a lecture filled with little exercises this is just deleting some of the things I write compared to a lecture. Monolith. Passive learning is great. Passive learning is the kind of thing that you can just put on in the background while you're cooking dinner. But I think really effective learning, you're using some combination of both of these. Can we just clear the whole screen? Because I can click this a bunch of times. Does my undo button work? Hey, undo does work. That's cool. We even have markers. Seem nice. Yes, this is the way I've decided to do this. So, I've passive learned these a bunch of times, but now let's try active learning it for the first time. The big difference there is just going to be, at every point, if there's anything I don't understand, stopping and working it through.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future, but what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network.
So something that I really love.
Learning.
So Free Blue One Brown, to give kind of full credit to this, is a wonderful channel, and something I really love is that they just wants to work through the structure of everything that it comes from, so that it is discernible and usable and is a kind of pragmatic tool rather than just a thing that you've heard of before. So machine learning is the biggest black box in our modern world, both in terms of it truly is a black box, like that is how it currently works, and also just the way we talk about it. Like the number of articles you'll see in the popular press that talk about machine learning that know nothing about it more than its name is higher than almost any other concept. Like, it's a bit like a lot of people will just talk about the internal combustion engine, and they know that they maybe know that there's combustion going on inside of it, but they don't really know what that means. Like, how does putting petrol in your car turn into power? That'd be an interesting video to do another time. This is a similar kind of thing. This is how does putting learning in a machine turn into the fact that you've been recommended to watch this video by an algorithm.
This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits.
So we're building all this boy.
This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the two videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many, many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants.
So, he's kind of going over this, but let's just do a little bit of disambiguation. Machine learning is a huge buzzword term. Various forms of it being used, honestly, all throughout human history. We have had machines that learn from before we had computers, arguably. Modern machine learning actually very often refers to some form of neural network. And we'll see this. Oh, that's a weird K. He's going to talk about this as well. So this is a subset of this. There, might even be a bit out here. Maybe there's some stuff that we wouldn't call machine learning that a neural network can do. Really generally what we mean by these is how to get a machine to, let's say, learn to do a complex task. Sorry about the handwriting, that's probably completely unreadable. And neural networks are a particular idea for that. They are passing outputs through something that looks a bit like a sea of neurons. Maybe it looks something like this. So at this point you could ask, okay, what machine and what task? And this word here, it's unreadable, complex. Let's just get it right here. This is going to be the key word, because actually what we're going to do is not solve complex tasks. I'm a big believer that you cannot solve a complex task. I think you can only solve a simple task. What we're going to look for is places where a task that we, a person with a finite attention span and a fallible memory, would find a task impossibly complex that a computer happens to find easy. That's been the real breakthrough of machine learning at the last. All the machine learning we have today is not necessarily doing anything that's that complex. It's finding a task which is a lot simpler for a machine to do than a human to do, and helping it along its way to do that task. So machine learning is anytime we're getting a machine to do a complex task. It's a pretty nebulous, undefined term. It's got a lot of soft edges. People will argue about which different things are or are not machine learning. Neural networks, more well specified, they follow a general form, although you'll find as many exceptions as rules. And basically, anytime you see a network, assume it's a neural network of some kind. Something like convolutional neural networks or long short-term memory networks are more complex architectures of this, maybe bringing in other factors, like, for example, in networks like this, we tend to pass information always forward. I'm not going to draw all the arrows. But in quite an interesting way, if you pass some information backwards, or some information back to itself, you start to get actually different things a network can do, and that would have a different name here. So when you see machine learning, just think complex for us, simple for a computer. I'm going to help the computer to do that task. When you see neural networks, we'll be looking at neural networks the whole way through here. I think that will become more obvious as we go. And when you see something network, assume doing some clever bit, changing out the pieces, maybe this becomes a triangle, in how that network functions.
But in these two introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number. Specifically, a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its active.
So we've got a little bit of, I don't know if you're seeing this aliasing here, but basically all of these are 0. Because when you write a number on a grid, you don't touch most of the cells in the grid. Then obviously, what kind of a factor of 4 smaller than that could be? Obviously, like right here, we've got a kind of spine of 1s. The whole square is filled in. Then at the edge, we've got like 0.5s and 0.8s.
Image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network.
I think that moment, I'm actually just going to play that again, where we take this makes perfect sense 2D grid, and we turn it into a 1D grid.
Here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer.
So yeah, we've taken a number, we've just split it apart. We could do it the other way, like we split on rows and put all the rows end to end. We could do it on columns. We're not saying that there's any particular form in how we do this. We could do it any number of ways. We could just randomly sort these. But we're turning what was 2D data into actually 1D data.
Layer of our network.
And we're losing quite a lot of information here. We're losing the fact that actually these two are basically the same. But we now have just a 1D list of numbers, and our question is, okay, with this really long 784 list of numbers, most of them are zeros, can we work out what number was written on that square?
Now jumping over to the last layer, this has 10.
Unfortunately, throughout basically all of these will be black, because if you think about it, these 8 represent, I think there's 16 in a row. 16 times 16, does that make 784? No. 24 in a row? 36 in a row? No? 24? Maybe. 30 in a row would be 900. 20 in a row would be 400. 25 in a row would be 500 plus 5 times 25, 625, 26 maybe? Doesn't really matter. But this is the first 8 of the top left corner. This is the last 8 of the bottom right corner. These will almost always be 0, because otherwise, you'd be writing down here. But in the 784, some of them are lit up, and those are the ones which correspond to the shape of the number.
Each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit.
So I don't want to skip ahead on things they're going to do, but let's work out the number of connections here. I think this is a really good question that I don't know the answer to off the top of my head. We have 784, I don't know why I'm switching to pencil, but fine. We have 784 nodes. I'm going to use slightly different, I'm going to use kind of graph theory nodes. 784 nodes going into 16 nodes. This is the structure of this network. It's these 16 by 16 that take inputs from all of these 784 and output them to one of 10. Goes to 16, and then that goes to 10. So how many connections between 784 nodes and 16 nodes? Well, every one of these 16 nodes is connected to every one of the 784 nodes, so it's just 16 times 784. Don't have a calculator handy, but I'm lucky. Chrome will just do it for me. So 12544 connections. So an incredible amount of information, and if you've watched any of my videos on this before, I like to think of this, and this might boggle some minds, but I promise it's worth it, as a position in a n-dimensional space in an n-dimensional box. And I like to map everything to between 0 and 1. So this is obviously just a 3-dimensional box. These are the size we actually see. So how many dimensions are there to this box? Well, there are 12,544 numbers telling you the weight on each of these vertices. There are then another huge number here, that's actually just 16 times 16. Way less, which is 160 plus 6 times 16, so 160 plus 5 times 16, 160 plus 80, 240 plus 1 times 16. 256. That's good, it's a power of 2, that's right. 256 vertices here. So we have this plus this, and then we've got, for each of these 16 nodes and these 16 nodes, they also have a bias. So we have 12544 plus 256 plus 16 plus 16. Honestly, it's basically just this number. We have roughly 1300 dimensions. The reason that we're not including this number is because we're not making any choice about this. This is just coming from the data. This is the pixel values for each bit of the data. And the reason we're not including these 10 is because, again, we don't have any choices about this. This is the output. It's just telling us a number between these. We're not doing anything special to it. But I lie. We do have also links here. So we have another 160 vertices. Still about 1300. So the state of this network, I'm going to write this really clearly. Let's I'm going to get rid of those numbers, but we'll keep it. So we have an input of 784, then 16 nodes to 16 nodes to an output of 10. And in these steps we have, come on, tell me the answer again. $12,544 vertices. So this is our input layer, which we're not going to do anything with, and this is our output layer, which we're not going to do anything with. I'm just going to use V for vertices. Then we have 16 times 16, which was what? It was 256 vertices. By the way, if you are a young person learning coding or mathematics, I really recommend a trick for keeping in your head and being able to easily get to the powers of 2, to count powers of 2 on your fingers, where you're just keeping track of the power. So 2, 4, 8, 16, 32, 64, so stopping now on 6. 6. 6. So 2 to the 6 is, I've already forgotten the number, 2, 4, 8, 16, 32, 64. 2 to the 6 is 64, 128, 256, 512, 1024, 2048, and I rarely have to go higher than that. Those powers of 2 come up all the time, and it's useful to have a quick way of getting to them. So you're just going up on each finger, and each time you're multiplying by 2, you can get really quick at it, and it's really useful. And then finally we've got 160 here. So let's actually add it up. 12,544 plus 16 plus 256 plus 16 plus 160. So altogether we have 12,992 variables. So the state of this system at any one time could be seen as a position in a 12,992 dimensional box. That number is so large that it's kind of impossible to picture it, but actually stick with it, because we're going to get that number down. I don't mean we're going to get that number down today watching these videos. I mean, if I keep working on this, and if you come across this video, it might be a year later and you might be like, is he still working on this? one of my ambitions is to get that number down until it's a point where we can really start to ask questions of like, okay, what does space? Because this is unworkable in. I do a lot of work in a 60 box. Now, in 6 dimensions, a lot of your intuition from 3 dimensions is dead, but a lot of it remains. So, that would be lovely. If we get it down to a 60 box, I'm laughing. I've got lots of experience working on that. I think it's more likely that this reduces down to a minimum, like hundreds of dimensions box. But, ooh, big rubber. Note to the developers of this app. You should show the outer circle of your eraser. It will help people see what they're erasing. So we are asking a question that seems kind of impossible, like, what's the best function? What's the best position in R? That's not how you draw R. In our space of 13,000 variables.
There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice.
By the way, this big question mark in the air right now, this is a completely reasonable thing for 3 blue, 1 brown to have done. This is maybe, I think we're heading to a different sort of reproducibility crisis in data science and the physical sciences, and anyone using these kind of networks where we keep making these arbitrary decisions of what size and shape our network should be, and we stop when we've got a good enough result. And that will be influencing our data a lot. This is just a complete... no one can teach you what size and shape your network should be, but it has an effect. And friends I've known who, mostly astrophysicists who've been working with machine learning, have just kind of tried it until one worked and then been like, oh, we'll just use that one then. And a lot of information about the system is both being lost and introduced by those choices, to the point where sometimes we might find that actually what we've done isn't learned anything about physics, but about our own choice of the system. 2 layers of 16 neurons isn't going to do that. 2 layers of 16 neurons is about as close to an understandable result as we're going to get. I don't know what the least network that this problem has been done with. This is a really standard problem. This is kind of one of the training problems for neural networks. This is one of the things that really worries me about modern computer science, data science, modern how we look at data. This is, by the way, how the robot which decides what things to show you on Facebook or Twitter or Amazon or Google works. And we don't know what it's doing because it cannot be known what it's doing. That fact took me a long time to grasp, and if you're watching this and you're like, yeah, that seems fine, either you've already known it for a long time, or I think maybe you've got more of it to grasp than you realise.
To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer.
So I should say at this point you might be thinking, like, why the hell have we turned this problem into a 13,000 dimensional space? That doesn't seem any easier. The thing about this is that this network is a really generalizable tool. And it can solve a really broad array of jobs, and we have a way of, when we first, like, if we first just put in random numbers, if we just choose some random point in this 13-dimensional space, we just say we're here, it'll do a terrible job. But we can then work out what we need to change to make it do a better job until it moves around to a point where it's like, oh yeah, now I'm actually doing a pretty good job of this. So the whole point of this is not that this is a very pertinent structure for the question, it's that it's a completely agnostic structure. This is a computation machine that could solve basically any problem. And when we first try it, it won't solve this problem at all, but we will then train it. It will learn. In a really, like, balls rolling downhill sense, we're not going to do anything particularly shocking to it. We're going to do something very much based in the mathematics that we're about to go through, but we're taking this completely agnostic general system and we're giving it that we know has the capacity to solve the problem, and then we're training it to get closer and closer to solving the problem. The problem again being recognizing which digit is which.
To how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has...
Just to back that up, neural networks were very much inspired by the brain, by linkages of many neurons to each other. Electrical pulses go through those neurons, that can set off electrical pulses going through the next neurons, and you get these cascades of information passing through bits of the brain.
Already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what did...
Just also to reiterate, neither he or I have said how these numbers, these brightnesses are being decided yet. If you're looking at this being like, I don't actually see what's going on here. I think his way of building this up is a great one. I think honestly me talking over it is probably making it less effective. So maybe if you're watching this thinking like, this is cool, but I'm not really following, maybe just go watch through this series, or even just this episode first once without me talking over it, and then come back and try again with me talking over it.
Digit this image represents.
Or never come back.
And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a...
I think this is a little bit of a red herring in that he's going to talk about like how we might do it, but it's fair enough to start to ask the question here, like, because what we'll see is how the network does it isn't very much how we will do it, and that can make it feel like, oh, the network's doing something crazy and unimaginable. We'll talk about that as we get to it.
The loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now in a perfect world, we might...
Honestly, you can do quite well at these problems by asking like how many different enclosed spaces there are, whether those enclosed spaces lie above or below most of the mass of the text. If we just actually look at the numbers, let's get rid of everything here. One thing that is often forgotten, particularly when we look at these simple problems, is that, you know, a human could do this reasonably well some fraction of the time. So we've got 0, 1, 2. Also, everyone draws these their own ways. 3, 4, 5, 6, 7, 8, 9. So, which ones have loops? We have bottom, 2 loop, loop at the top. Arguably, this might be part of why numbers are written this way. Which ones have stems? We have stem throughout, stem throughout, stem at top, stem at bottom, stem at top. Stem throughout. I'm going to be pretty arbitrary here. But kind of straight line stems we've got in a few places. Maybe we actually don't think that the 6 and 9 have straight line stems. Maybe we say that these have like close to vertical stems. We could then ask which ones have curves. Curve at top. Probably for most people curve at bottom. Like I like to draw my lines straight. You can choose how to draw them, but either way, nothing else has this form. Curve throughout. Curve at bottom. 2 curve. That's ugly. And then 2 curves separated top, bottom. And what have we got here? Well, we've got 2 curves separated left and right. Also, arguably, we have a second stem here that I've ignored. And then finally, we have horizontals. Horizontal here, horizontal here, horizontal here. And horizontal here, although we often draw it as a bit curved. So if we wrote good algorithms for finding loops, I'm going to run out of space if I do it this way. Loops, curves, verticals, and horizontals. And then we take all our numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Arguably 0 is a loop, and we'd be better off calling it a loop. Let's call it a loop rather than calling it 2 curves. That's much more sensible. This, by the way, isn't really what this algorithm is doing, but let's kind of think through what's going on. So 0 is just a loop. 1, no loop. 2, no loop. 3, no loop. 4, 5, 6 has a loop. 8 has 2 loops. So maybe rather than saying, we'll see, it has 1 loop. Has 1 loop. Has 2 loops. Has 1 loop. We could even say that this has a loop at the bottom, and this has a loop at the top. And even that this one has a loop at the top, bottom, and a loop at the top. So an algorithm that could find loops could actually tell you if you were looking at one of these pretty reliably. The only difficulty might be something like, is a 5 maybe a loop? Like, I could draw a 5 like this some days, if I was having a bad day, and I could draw a 6 like this. And then neither of them are perfect loops. And a lot of what the neural network is more effective than this brute force method is in these edge cases. Still though, like, you know, if I wrote a loop finding algorithm, I'd probably find most 0s, 6s, 8s, and 9s pretty reliably. I could even then say, okay, let's go looking for curves. So I'm actually going to say 0 doesn't have curves. Well, it sort of does. I'll give it a little thing. 2 definitely has a curve. It's one big curve. not even saying which way around here curves are. Curves are actually almost always in numbers pointing to the left. 3 has 2 curves. I'm going to use like they're pointing the way if they were the mouth of a beast. This is what they would eat. 4 has no curves. 5 has 1 curve at the bottom pointing to the left. 6 is the only one with a curve pointing to the right. And 9 has 1 curve pointing to the left. So again, if I wrote this code relatively reliably, I'd capture 9, 6s, 5s. All of these would probably be possible to tell apart. If I go looking for verticals, 1 has 1, 4 has a whole, no that's not 4. 4 is the next one, it's got a whole 1, and then it's also got 1 at the top. It's got 2 verticals, it's the only one with 2 verticals. So actually let's just say that it's got 2. Well no, actually that's not the way we've done it elsewhere. It's not very much in the 4 place, but good enough. 5 has just 1 little one at the top. 7 has a slightly diagonal one. And 9 has questionably 1. It also could be questionably this curve. Then finally horizontals. 2 has 1 at the bottom. 4 has 1 in the middle. This notation has already gone insane. 5 has 1 at the top. 7 has 1 at the top. No, let's just make that a 1. Ooh, smaller rubber. 8 has none. 9 has none. So if we had a good algorithm for finding these different features, there's a lot that separates all the digits. In fact, maybe you start to see like, okay, maybe this is why we use this school of digits. Each one of them has their own quite unique patterns here. Particularly things like 0 and 1. 0 and 1 are sort of infinitely tellable apart. 1 arguably gets harder when you start including stuff like this. Unfortunately, stuff like this is exactly where the problem gets more difficult, because now 1, if you draw it like this, suddenly got a horizontal at the bottom, and maybe a second vertical one at the top, because maybe this registers as a vertical. So the foibles of handwriting is what makes digit recognition such an interesting problem. It's not too difficult to do in the abstract, but then handwriting often varies, like things like geographically. It can vary based on locality of school teachers. Some school teachers will teach their students to always draw a 9. I don't even know how they do it. Like that. Like that. I think if you're drawing a 9 like that, you probably draw it from below first. That freaks me out. That's a 9 to me. But one issue that I sometimes get is if I'm really unlucky, my 9s can become 7s. My 2s can't really become 3s. 3s and 5s could probably be a little bit difficult to tell apart if that gets small enough. Any others? I guess my 7s could just about become a 1, but there are reasons why we have, and I think a really unlucky 3 could look a bit like an 8. But there are reasons why the digits are so unique. Emmerich, you asked, like, why would this be useful? Like, one thing might be that I might be doing something like writing a lesson plan here, and I might not want it in my handwriting forever. I might want it translated into text. So I might write the words loops, curves, vertical and horizontal in a lesson, and some students might want it, rather than it being in my bad handwriting, in like digital text, Unicode LOOPS. So it'd be fantastically useful to have an algorithm that translates words to text. And in fact, sketch. I don't want SketchUp. There's a lovely thing. Quick Draw? Yes, Quick Draw. This is a continuation of this technology. This is a Google thing that can recognize drawings. Surprisingly reliably. Good enough. Fine with that as grapes. What does it think it is?
I couldn't guess it.
Oh, it didn't work out my drawing of some grapes. That's a shame. Bit long. It's not perfect.
Sorry, I couldn't guess it.
Wow, I'm doing terribly.
Sorry, I couldn't guess it.
Have I broken this somehow? It says a poor show from this thing that normally I found to be pretty effective. What does an oven look like? God, let's have it open. And inside there's shelves, like racks.
Sorry, I couldn't guess it.
Come on. Okay, the app is completely broken and actually the whole method does not work. This used to work, I don't know why it's gone. Draw yoga, really? So someone, arms and legs crossed, on a mat. I'm not saying that these are perfect.
Sorry, I couldn't guess it.
Okay, what did you see? So it's possible, and this is kind of fascinating itself, it's possible that the fact I'm drawing with a drawing pad, that's enough to throw it off. And that actually shows you the fallibility of these things. Like, I think we'd look at this and be like, they're basically the same, but one difference is that I can draw much quicker with a drawing pad. It's interesting that it doesn't much care if the sheep is pointing left or right. Let's just try again with just the mouse, in case. Come on, it's a circle. It's just a big circle. Apparently I draw like a bizarre non-person. No, I think the app's just broken. Great. Thanks, Google. Useful for my lesson plan. Again, I think the use of this that has been most important to us, which looks like quite a different task, but is basically working on the same thing, is recommendation algorithms. How do you map any particular user who's busy? So a user is thinking about something. A user is thinking about something like, will bridges collapse? They're worried. They're worried whether or not they can drive their Google recognized this picture of a person thinking about a bridge collapsing. They're worried about whether or not they can drive their heavy truck over a bridge. So they type in to Google something like bridge collapse. This is, in a different way, a sort of something a bit like handwriting. It's their particular way of expressing this idea in their head. Poor Google, or Twitter or Facebook or whatever, has to be like, oh my god, they wrote B, and then they wrote an R, and then they wrote a few other things, and then G and E and space. Like, what is it that they want? Like, Google's a bit clever in this, but that's basically the question it's asking. And so it has to choose, like, this user, who I know a bit, like, Google knows you a worrying amount, has to choose, like, does this person want a disaster movie? Do they want an engineering textbook? Do they want a law? Do they want to see what the, that's an ugly L, what the government advice on this is? Do they want something to do with a card game? Do they want the obscure 1951 French film, which is called Bridge Collapse? Do they want the stock market collapse? In Cambridge. If I'm typing that in, maybe that's the thing that they're like, oh, that's what the person wants. They want something about Cambridge and they want it to be collapsing. And in exactly the same way, Google has to look at what you've put in, what you've kind of, as far as it's concerned, drawn. Because what you're drawing here doesn't look very much different to a machine learning algorithm than the words you use here. And it has to go, aha, this person actually wants law. I do chaos theory all the time, every day. This is chaos theory. So poor little Google robot. It's halfway between a free blue, one brown, and BMO from Adventure Time. Poor little Google robot has to link you using Bridge Collapse with law, and they have to link you with, if I'm watching in the UK law, and I have to link you with the current UK law. And they have to make all these decisions, and they're using the same process. They're simplifying the information you've put in. So they've probably worked out that this is a word and this is a word. They've also probably worked out that you tend to read, like I see this, I have different browsers that I'll use for academic work and for shopping and for like playing games, and I'll get very different results on them. Like if you tend to spend your time online reading a lot of news and shopping, they probably won't give you the engineering textbook. Whereas if, like me, you spend most of your time online watching YouTube videos about maths, they probably will give you the engineering textbook, or in my case, they'll probably give me the 1951 French film, which I always appreciate, even if I don't actually want it at the time, because I always love to know stuff like that exists. Exactly the same thing is happening when you... So that's a nice Google example. Exactly the same kind of thing is happening when you go on Facebook. So when you go on Facebook, or whatever your preferred social network of choice is, let's say it's text space. Now this is already someone's icon, isn't it? That's basically Tumblr. Let's make it a different colour. You go on textspace.com. This is going to seem like a religious thing, isn't it? If anyone sees this thumbnail, they're going to be like, what is he talking about? You go on TechSpace, and poor TechSpace, wow, that's ugly, has to decide what you want to see. Won't this information be vulnerable to be sold to corporates and stuff? Yup, I think one of the largest human rights violations happening on a global scale right now is how little regulation there is on this information. And a lot of that regulation that does exists at a level which can hurt individual researchers and creators, but tends to favour basically, I don't think Facebook and Google are the criminals here. I don't think anyone's a criminal here. Everyone's very much within the law, but some people are setting the law. I think the real issue is companies making and selling ad bots. They're the people who I think we might look back on in 20 years and be like, why did we not regulate them? But when you log onto this, poor text space has to be like, well, I know this person has interests like they like looking at pictures of birds. They like looking at pictures of their friend Steve. Not in a... All my friends called Steve right now are going to be like, oh my god, does Steph really like looking at pictures of me? And they absolutely hate hearing news about food. And this bot, its job is to give you stuff, is to choose which one of these to show you. And its job, which one to choose to keep you engaged. And it's got the same kind of problem. It's got this relatively basic, low-level information about you that looks to it about the same as a handwritten digit. And it's got to be like, okay, which thing for this person? And what it will often do, and this is one of the things that I think is really dangerous about social media, and we're seeing right now. Social media is such a wide term that there's no simple good or bad, and I don't think we should look at it that way. But it loves to show you things you hate, because you tend to interact with things you hate. You get angrier and angrier. And you keep on scrolling, you keep on being like, I can't believe people are being so ludicrous about food right now. And if it were to show you a picture of Steve right now, you might calm right down and be like, I guess the world's not so bad. Yeah, there's a lot of stupid news about food, but at least Steve exists. But it's solving the same problem. It's looking at you with your kind of nebulous, unclear, bad handwritten information and trying to work out what will keep you on the platform. And sometimes it does a terrible job. A lot of the time it will be showing you stuff that you don't care about at all. But actually one nice thing about a social media feed is, one nice thing for the algorithm is you can see like 5 things on there at once. You can have like a video, and you can have something a man said, and you can have an extract from a politician's speech. And if you don't care about the politician's speech, but you like the thing your nan said and you like the video, you're probably pretty happy looking at this thing on screen. So the algorithm can be a bit wrong some of the time. That's okay. It probably shouldn't show you stuff that will actually make you leave the platform. Like, it probably won't show you... Well, actually, no, it might show you an article saying that text space is bad for your health, because, honestly, you might read their article and then share it with your friends and then talk about it on the platform. But it's doing exactly the same job. It is working out from this kind of poor information what it should show you. And all the while on that site, also ad bots are doing the same. They're looking at the information it has on you and deciding, okay, this person we can sell a DNA test to. This person we can sell a a car to. This person, we can get to vote a particular way. Human beings aren't simple. You can't ever write down the algorithm for a human being, but you can write down relatively simply a shockingly effective algorithm for most human beings most of the time. And if that sounds scary, I actually think it's one of those rare times where it is and it should. This is a really important point. The algorithm can abuse human behavior. It can do so really directly. Like it can hit on your deepest fears or your insecurities. It's quite difficult. Let's say I can do it very well. Humans can abuse the algorithmic behavior only indirectly. So it's not the case when I say that ad bots are a thing that we should be really thinking about regulating. It's not because the people producing ad bots are making some evil product doing a particular thing. It's that I just saw your joke. It's that the ad bot is designed and told abuse human behavior, and it goes off and does it. It can only do such a good job of selling you a car. So if you tell it sell car, it will use kind of deep Freudian psychology. It will look into the middle of your psyche. It will find your past traumas, not in a direct way, and it will pinpoint them, and then it will do a pretty crappy job of selling you a car. Because the human brain is quite learnable. But if you then wanted to use that algorithm to do something really harmful, you'd actually find that it's a really blunt tool for this. Because if you tell the sell car algorithm, and this is the thing that people find, if you tell the sell car algorithm to sell different car or to sell bike, the poor thing's like, nah, I don't know how to do that, man. Why do these keep disappearing? Yeah, this is how modern dating apps use this. This algorithm, this broad structure is used in almost every part of modern life. If you go online to order a pizza, if you go to a delivery website, this algorithm will, some variation on this algorithm. It's not like each website has its own one. Some variation on this algorithm will be deciding which restaurants to recommend you. If you go on a dating app, some variation on this algorithm will be recommending which people you see. It doesn't have any ulterior motive. It's not an evil algorithm. It's basically a dog. It's the dog that brings your slippers every morning. Don't know why I'm drawing a terrible picture of a dog. It's the dog that brings your slippers. It just so happens that instead of bringing your slippers, it's bringing you the information that you see when you go online that you use to build your worldview. And this means that all of us, you and I, in our own individual ways, are as susceptible as we have ever been to being channeled into a worldview by lack of context in the online world. This is one of the reasons that I'm making this strange YouTube, Facebook, Twitch channel. Because I can see all these ways in which people are so channeled in our world, and I think that because the way it's happening is just some interesting maths going on underneath, I think it's really important to help other people understand that. Yep, you can write an algorithm. Like, let's say you have, you've trained a little slew of bots. Stop deleting my eyes, app. Let's say you have 10 bots, and they've all been trained to sell people different things. You might then ask, okay, which bot do I use? Like, new customer comes along, which bot do I choose? I don't know. I'll make a bot, which chooses bots. And then you could, like, actually maybe there's 10 of those, and you can write another one which chooses which bot for that. Like, this thing can... There's a law of diminishing returns at some point, like at the point where you're making a specific, bespoke robot for each individual person. When I say a bot, I don't mean a physical thing. What I actually mean is a position in this 13,000 dimensional space. Or actually, in the case of like the ones that are doing a Twitter algorithm, it's not 13,000. It's millions, billions. 1 times 10 to the very big. This is how we find things on the internet. And it's, at first you're like, why is it that way? But you're like, oh, actually it's because the internet. You know, we're looking at the world through our telescope. And we're seeing just some small patch of sky. This is all we have a picture of. And we're trying to build up our understanding of the world just based on that. Because also, one thing these algorithms do is they make it hard to look at a very different patch of sky. So we're looking up here, and that's because, in part, the algorithm is our little bot, the slew of bots that are attached to us are pushing one way or another. They're saying, no, keep looking over here, keep looking over here, keep looking over here. Have you noticed that actually, if you squint, I promise I'm better at drawing than this app is making me. If you squint, those stars look like a car. And they actually don't really want you to swing the telescope over here and look at a different patch of sky. Even, like, maybe, quite possibly, there's a thing that looks like a car here. But they just don't know, because they've learned you, and they've learned your little patch of the internet, and they've learned car. And slipping into the unknown is just terrifying for them. So this is the world we live in. We are actually quite pinned in place by the normally quite chaotic and completely random machinations of those algorithms which decide what we see online. And it's very hard to get out of them. And one thing I've been researching in my... Well, this is how memes work. If you go to somewhere like Reddit, this is how things are being shown to you on Reddit. This is how memes are developed. This is why memes are so funny. And one of the possible ways to make a robot that shows you a particular kind of content is to make a human that shows you a particular kind of content. And that's what people are voting stuff on Reddit are doing. This is not some unique thing that just exists in the world of machine learning. We're doing this all the time. It's just always the question of there's too much information, to quote Sarah Lynn from BoJack Horseman, there's too much man, so we need a way we need a filter so let's train a bot. This is the path of the modern internet. I mean, at my most paranoid moments, I fear that, but I'm not saying anything that isn't in the public sphere. I'm not saying anything that is politicized or controvertible. This is just how the maths of it works. That's one of the things I think is so crucial to learn about this. Like, there's a lot of maths which I don't think the FBI are going to go after me at any point, but it's quite possible that that some publications might not want to publish my stuff. I sometimes think about, I write essays sometimes just for the internet, sometimes think about sending them to newspapers and things like that. Some of them are going to be like, no, we don't want our users realizing that this is used on our website. One example that I think is really interesting is the BBC, who I pay my taxes. I actually don't pay taxes, but that's because I paid so little. So I'm allowed to be mean about the BBC. I pay whatever taxes I'm supposed to pay, which is none, which is nice. The BBC use this to decide what is on their news homepage. Which is just an algorithm that's just trying to make sure that you, the individual, are linked with news that you like. Oh, that's a terrifying person doing a thumbs up. It's not much better. And it changes what your view of the world is. Because the information you like stems from your view of the world, and your view of the world stems from the information you see, and the information you see stems from what the robot tells you, and you get a feedback loop. We're not powerless in this system at all. We have a lot of agency, but we don't have full agency. Like, you cannot find something on the internet that you cannot find. At this point, you might be thinking, like, God, are people going to be using this for tricking people into voting a certain way in elections, or are they going to be using it for making people buy things they don't need? And the answer to all these questions is yes. They are. Not very effectively, but they are. And they'll get more effective over time. And we'll even start to see what you might call speciation. So let's say one group starts out 15 years ago, and they regularly type in food to Google. And then over time, one of the most common stratifications here is that some people go towards fast food, and some people go towards slow food. And for a while, the thing you get when you type food is just, you can kind of see this dichotomy. But eventually, the in-between space gets smaller and smaller. And that tenuous little link breaks. And now when people type food into Google, the people who go looking after things like slow food get the stuff that grows out of that. So maybe they get it'd be crazy to make any point that this isn't also a very wealth type version. Food was kind of a bad choice to pick for that, but wealth and place in society is often one of the things that speciates you here. The slow food people might be getting wine and yeah, let's just own up to the fact that this is such an economic thing, and adverts for housing, and honestly, they might be on the kind of websites where they get loan offers and things like that. And to make this point, I'm going to commit entirely to this kind of very economically motivated reading of this. The fast food people might get beer. That doesn't seem like a completely unreasonable thing to say. And sports, because it's lovely to have a pizza and watch a sports game or something like that. It's a joy anyone can enjoy. And eventually they might get things like betting websites. And also, both of these groups are going to be getting the news. If you read about, wow, that's really ugly font. If you read about sports, you're going to be getting some fraction of the news of the world. Sports and even beer and betting websites do not exist in a vacuum. But their news, whilst it seems singular to them, it's the only thing they can see. Contains different information for two different groups, and their worldview starts to split further and further, and actually these two groups push away from themselves. It's like there's a repulsor in the middle of them saying, get out of here, go away. That's when we get speciation, when there's actually forces pushing, even if those forces are just the weird machinations of the flow of information, forces pushing two groups away. You could think that you're unique only to find out that everyone has the same personality, but you could also think that you can see everyone's personality. You could think that this is the world, and these people could think that this is the world, and any time that they happen to be recombined, you have a difficult reconciliation of like, oh, there are other people living different lives. If we're entirely made up of physical reactions, aren't decisions meaningless? It's a good question. It's more than I can answer. Have to make your mind up on that yourself. I certainly do not subscribe to kind of the deepest everything is meaningless nihilism. I do think that we are much more our circumstance projected onto the world than we are some magic judge who makes divine decisions about what the world should be. But we are a physical object, and we are a decision-making object, and we do get to make choices. It might be that those choices are the outcome of a bunch of balls making their way down through a Galton board, but we still get to make choices. I'm going to carry on with the video. Isn't it impossible for anything to have happened otherwise? Well, yeah, I don't think I personally don't think anything happens that isn't the result of let's just stick this on screen for a sec. Axiomatic law, which basically means physics and mathematics. And I'm just going to call it physics. I'm going to use my own definition of physics, which is physics is mathematical axiomatic law relevant to our world. Things can also happen by chance, and in fact I think this is the vast majority of things that happen. This is a small little thing that has some effect. And then they can happen by feedback loops. Now, feedback loops are just born out of chance, but some situations, when they happen, tend to keep happening, keep causing themselves. And this is why some things that should just occur by chance actually keep on happening. This is why, for example, I'm going to keep on getting like socio-political about this. This is why systems which say, oh yeah, everyone can go to university now, are still feedback loops which encourage the wealthier to go to university. The thing doesn't exist, like in a completely flat system where everyone has the same chances. You can still get feedback loops which mean that some behaviours happen again and again and again and get stronger, more and more people get swept up into them, and they become a culture. I'm 6 minutes into this video and I've been recording for an hour and a half.
Hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in...
By the way, if anyone...
Say,
So, anyway, I should say, most of this I'm recording it live and I like having people come into the chat, but I'm sort of recording it for the future. Like, it's more of a podcast that I'm recording onto YouTube than a live stream. Obviously, it is a live stream and I really appreciate people coming in and interacting with it, but a lot of who I talk to on stream will be potential, maybe one day. Honestly, I'd be surprised. I'm 50-50 on whether they will ever exist, people who come along and watch this video in the future. So a lot of who I'm talking to will be talking to them. So if you are them, I see you. I don't know who you are. I don't know what the world looks like where you're watching. How is it? How's everyone doing? If you are them, maybe skip back to the last time that I was talking about the video and remind yourself what I was talking about, because we've come a long way. We have this network that's being given this handwritten digits. It's feeding those through a few layers with some arithmetic sums between them, and we're hoping it might capture important features in the data and use those to say, like, okay, we have a top loop and a bottom loop, maybe it's an 8. We have a vertical and a horizontal, maybe it's a 4. That's not quite what's going to happen, but that is a fair way of looking at the action of these networks. They're probably doing some combination of that.
A loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in...
Just to say, like, we're kind of in the world of what neural networks can do here, but if you have in pixels a loop, one way you can recognize it is you can choose a random point, look for all its neighbors, and see if you've touched all pixels, and if you haven't, if you've stayed within some region, you're in a loop. It's not perfect, it has edge cases, but recognizing a loop, if you actually just had to do it from scratch without relevant sort of things, is not that difficult a programmatic challenge. Again, it's the generalizing, it's the everything working all at the same time.
It's 1 or 4 or 7. Well, that's really just a long edge. Or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able
So one thing we haven't really talked is what's going on at these loops yet, but these loops basically are passing through a function like this, which is 0 at one side or 1 at the other side. So basically asking, is something true or false? So this structure, where you ask like, is there a loop? Is there a vertical? Is there a diagonal? You could be like true, false, false, and turn that into, well then it'd say 0.
To detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign...
So, I think, at the moment, not fully specified conjecture, but I think a fair conjecture, and the conjecture that's kind of being made here, is that somewhere in this 13,000 dimensional box is some combination of instructions that you can give to each of these nodes, each of these vertices. Oh, that's ugly. Let's get rid of all those dots. I guess it doesn't like dots because it's just more information for it to store. It would rather I didn't make a dotted line because it, if it wants to keep the undos, that's difficult. So we want to find some region in this box. And the conjecture is that somewhere there exists a well-functioning machine that does this. And if we just choose a random point, it won't at all, and we just got to ask the question of how do we find something that, if we start at a random point, takes us on a path to that well-functioning machine. Except for, again, this is a three-dimensional box, and we have a 13,000 dimensional box.
A weight to each one of the connections between our neuron and the neurons from the first layer.
So these weights are the vertices dimensions. Now, actually, these aren't numbers between 0 and 1, but we can map them to numbers between 0 and 1 by using a function that maps numbers between 0 and 1 to minus infinity to infinity, like, I think tan to the negative 1 of x pi should be, I could check this, I'm not going to, should be a function that looks something like this. And thus, for any number between 1 and negative 1 we put in, it will give us a number all the way from minus infinity to plus infinity. We could doctor this a bit more to be a number between 0 and 1, but it's completely doable. And that's what I'm talking about when I when I talk and think about this as being that box between 0 and 1. We we can just define some functions to map it until each of these numbers can be represented as a number between 0 and 1.
These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red
These are lovely. That's all I have to say, those are lovely.
pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about.
So that's
And if you really wanted
because
to pick up
in this, I'm going to call it a mask, in this mask we're using here, this little rectangle here is all 1s, everything else is 0, so this basically just registers if there is a line here or not. So if this rectangle were instead here, if it were a vertical rectangle, it in general wouldn't register anything for a 7, but for an 8 it would be kind of surprising if the 8 wasn't passing through that region. So you could say this as it's asking if things are falling in this particular region. Now when you get more complex patterns like the one he just showed where it was red and green all over the place, you're asking kind of more complicated questions, or even one way to see it is you're asking many questions at once.
on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding...
I think this design your own is actually really nice and helpful. Like this one, those negative pixels are going to give you a big value when these are 0, and a small value when they're 1. So it's actually specific. It's checking not just that there's a thing going across, that there's a thing in this region, but that it's going across. Like if this whole thing were just filled in, the negatives would cancel out with the positives. Where this gets difficult is like if you look at this grid, the 7 could be anywhere in it. It could be up here. It could be down here. So just doing that alone wouldn't do this, but you know, we're on a track.
Pixels are darker. When you compute a weighted sum like this, you might come out with any number. But for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function.
Oh yeah,
Also
I'm
known as
using a
the
sigmoid for this. It's inverse sigmoid.
Basically, very negative inputs end up close to 0. Very positive inputs end up close to 1.
So let's just
and
write
it
this
just
down because
steadily
it's come up a
increases
lot.
around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like negative 10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active.
So one way to see this is actually we're doing sigma of the, come on, I just want 2 eyes, there we go, of the sum of all of the things from the previous layer, which is 1 plus e to the minus, we can do b minus the sum over wi xi, it's not going to like the i's, to the minus 1. The eyes stick around for a bit and they just spit. I don't understand this software. Like, why is it doing this? So this is actually what we're passing it through each layer, where this is the sum of all of the weights, all of the coordinates associated with each vertex. and with this extra bias which belongs to the node.
And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of...
As we've seen, actually, this number completely dominates the number of dimensions.
weights and biases associated.
Though maybe doesn't dominate the complexity of the
All
problem,
said and
because
done,
those might be
this
less
network
important
has
dimensions.
almost exactly 13,000 total weights and biases.
Oh no, I was wrong. There are biases associated with the output layer. I'm good at maths.
13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about...
Can you have some soup?
about learning, what that's referring to is getting the computer to find
Yeah,
valid
I like
settings
that.
for
Write
all
that
of
down.
these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the
This is
second layer
actually
picks
something
up
that
on
I'm doing
N,
in my spare
the
time,
third layer picks
going
up
through
on
and doing it
N,
all by hand.
etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you
So this is, finding the weights and biases is what I'm calling, or what I like to think of as finding the position. In those n dimensions.
to anticipate. If you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks.
How do they write
Organize
it?
all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here.
We've got the matrix times by the activations plus bias.
By the way, so much of machine learning just comes down to having a good grasp of linear algebra. So for any of you who want a nice visual understanding...
Very much recommend this to anyone
of what
watching
matrix
this,
vector multiplication means, take a look at the
struggling to
series
keep up
I
with
did
this.
on
This
linear
is,
algebra.
by the way, I think if you've got this far, you've worked this out. Although this is not that complicated, this is the forefront of modern computer technology. Don't be scared off by it, but it is hard. It's not supposed to be easy. It's as hard as it is because that's the cool tool we're making, we're working on. It's fine if you find it hard. That's not a sign that you're doing it wrong. It's just hard. Some things are just hard.
Especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we
Actually, this
represent
is
it by
a...
organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. Then as a final step, I'll wrap
I might
the
stop using this
sigmoid
tool. It's
around
just
the
really
outside
ugly.
here. And what that's
It's not
supposed
just
to
me.
represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these
Let's try this
vectors
again,
as their
bigger.
own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated...
This is a really good way to think about it. We're basically chaining many functions. And if you chain many functions through functions, all you get is functions. They just have a lot of complexity.
Function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and a sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing. Now is the point I suppose I should say subscribe to stay notified about when that video...
Okay, I'm going to end that there, and I'm going to go get some lunch. If you joined, thank you for joining. If you didn't, what are you doing with your time? No, obviously, if you didn't, doesn't matter. 50-50, because whenever I say I'll do something later, I don't do it. 50-50, I'll come back after lunch and watch video 2. So maybe see you then.